So you go through all of the data to see. Go through all of the data. Sorry.
I see. It has to do with the Wi-Fi. So, I mean, there's. Don't lower the bitrate. Huh? Don't lower the bitrate because that will just reduce the quality of the video. Yeah, exactly. And at least in this case, eventually it will get better. Yeah, yeah, okay.
Yeah. So there's extremely stretchable. Exfoliated is this weird that they just gave me.
Reminder of things that are on your plate right now. There's a homework that's out there. It's been out for a week or so. It's due in a week. Entirely about learning theory and I think you've started. We'll get to any questions about that at the end of the announcement. There are the project intermediate status reports that are due next Thursday. I think I've given feedback to all of you who are doing the exploratory project. If you haven't received any comment on Canvas regarding the exploratory project, send me an email or something. I know that some of you wanted to meet me at office hours but couldn't. So if you have questions, we can talk about it. I haven't yet assigned the points for the competitive project yet. I'm still trying to create a spreadsheet that I can map your name on Canvas to your name on Kaggle. And as easy as you might think it is, sometimes it gets tricky. So I'm a little slower on that. Anyway, so the intermediate status report, as I said last week, is basically a way for me to understand what you've been doing in the project so far, or for the project so far. And it's a way for you to kind of, if you've not done much, you use the you know how it works. So also I would like to know what your plan is for the rest of the semester so that you can spend a minute or two thinking about a plan. Roughly, both kinds of projects, I expect the same sort of information, namely what have you done so far, what's your plan going ahead. But in particular for the exploratory project, I would like to know what you have specifically done with respect to the project. In many cases, I would like to understand, for example, how you plan to evaluate any systems that you have if you're planning on something. Also, you should have all your data, so I would like a more, somewhat more detailed description of your data and any features that you may have planned. And also, I would like to spend a little bit of time describing your experimental setup, because that is going to be important. As much as machine learning involves a lot of math, it's also increasingly an empirical field, which means you need to follow the ideas and approaches that are developed in experimentation, in experimental science. So you need to be, in the case of the project, for example, you need to make sure you have a training set and a test set, and they don't share any examples. You need to, before you even start training anything, you need to have a clear notion of how you measure accuracy, for example. How you measure performance. It could be accuracy. In some cases, some projects involve regression. It could involve something like mean square error. Or however, maybe there's an application that you have where the application dictates success. So you need to decide that before you even start building models, because otherwise you might be very, very tempted to using your models to define success, and somehow making, at surprise, surprise, the models that you train look the best. So that's kind of a tempting thing to do. So it's good to commit to an evaluation plan before you start training. And I would also like to see some sort of baselines, for example. What's a reasonable or unreasonably brain-dead system that works on your data? For example, if you're doing classification, a baseline that I always look at for any new classification task that I'm encountering is majority label. If I predict the most frequent class for every example, how bad is my system? Because think about it, if you have a classification mechanism, if you train a classifier, you put a lot of effort, you brainstorm some features, you train maybe a fancy neural network, and this is such a complicated network that it takes 3 days to train. And at the end of it, it doesn't do as well as the simple majority baseline. Something's wrong. And you might be surprised, but sometimes it happens. So it's good to know the majority baseline gives a sense of how hard the problem is. Sometimes the majority baseline also tells you that maybe accuracy is not a good measure. A good example of that case would be, let's say you have a classification task. And by the way, this is, I'm talking about the exploratory project, but this is general advice for, say, life, or at least the machine learning part of your life. Imagine you have a classification task, and you find a data set where there are 99% of the examples are labeled negative, only 1% of the examples are labeled positive. Or even worse, let's say 99.999, whatever, 1 in a million examples are labeled positive. Now, what's the majority baseline there? If you predict the most frequent class. That can't be hard. Is it high? Is it low? Anyone has hands to raise? So the setup is you have a data set with 99 negative examples and 1 positive example. And I predict negative on all of them. What's your accuracy? 99%. If your data set has a million examples but only 1 positive example, that's an even worse situation. You get extremely high accuracies, but clearly that's bogus, right? Clearly there's no learning, and so the majority baseline in some sense tells you, it tells you something interesting about the problem. It tells you if your data set is skewed, maybe accuracy is misleading. High accuracies really don't reflect good performance, so you need to rethink. You might need to measure other things like precision or recall. I know that some of your projects have this property, so think about this. Right. For the competitive project, I've been keeping an eye on the Kaggle leaderboard, and I see that many of you have been working on this. And amazingly, the performance in the top maybe 10 or 15 entries in the leaderboard are all clustered around 88 or 89%, and most of them involve the Perceptron algorithm, which is cool. There are some of you have tried decision trees of depth, maybe 4 or something, because that's roughly how much you can push it before the CPU starts crying. And I don't know, do decision trees work well on this data, like even depth 4? Has anyone? I know someone has tried it. If that person's here and wants to admit to it. Yeah.
I've tried it for depth 15
And
61%.
61? Yeah, so it's interesting, right? So there's something funny going on. The Perceptron is a linear model, and it gets 80-something% accuracy. A decision tree, which allows non-linearity, does much worse. But if you think about it, you are using only 15 features, or there's some scaled version of that. So that's really an interesting trade-off. So I encourage you to try that out. In your report should tell me, again, no more than 2 pages. The report should tell me what you tried, what you did, what works, difficulties you may have had, what you plan to do for the rest of the semester. And as I said earlier, I need at least 6 different non-trivial runs. So a different run, if you train a perceptron with, say, one hyperparameter choice and you train a perceptron with another hyperparameter choice, I wouldn't count them as different runs. They're the same algorithm. So I want 6 different non-trivial runs, one of which could be just a minor variant of something else. So for example, the 6th one could be, say, for example, you try decision tree with entropy, and then you try decision tree with majority error, if you want. Or the 6th one could also be something like something where you use some off-the-shelf machine learning tool on your data to get a sense of how well it works. Any questions? Yes?
So you always say that the 6th one when you're talking about different variants we can use. What is okay for the 5?
Let's see. So you have Perceptron. You can, for example, I would technically not consider average Perceptron as a different algorithm, but I'm willing to let it fly. Decision tree maybe. SVMs. You can do some sort of an ensemble. I think bagging or just random forests, for example. We will see logistic regression in a while. And while you will not implement logistic regression for your homework, you will derive it, maybe time permits, and you will see that the algorithm for logistic regression basically is SVM or Perceptron plus epsilon. So it's almost the same. Another possibility you could try is you could try various feature transformations. They count as different models because even though you use the same algorithm, it's a different class of functions you're exploring. So pick some subset of these that work. You have access to the raw data, the text. Now, if you want to invent new features, you can do that. Like over the weekend, I had some time to kill, and I was playing with some features that I thought was very clever. It turns out not so much. So you can play with ideas. You can play with features. We will have at least 6 or 7 different learning algorithms and their variants. For example, if you want to try something like a boosted, here's an example algorithm. You have a bunch of decision stumps that you train on subsets of the data. Maybe you train not 1 or 2, but maybe 5,000 decision stumps. Each decision stump predicts positive or negative label, right? Now, the standard ensembling method could be you just ensemble them. That's one method. Another one could be by standard ensembling method, I mean you just take the most common label. Alternatively, you can take your decision stumps, all 5,000 of them, run them on the training set again. So you get 5,000 predictions for each training example. Each prediction is a 0 or 1. It looks like a feature vector. You can train a perceptron on top of that. So you can train a perceptron, a linear model, to ensemble decision stumps. That's a very different kind of a model, and I expect you'll be doing something like that in your next homework anyway. So you can plan these things. So you can do a lot of fancy things around ensemble. Yes?
So for the 4 that are from in class,
5.
say decision trees, or yeah. Do you mean ID3 or do you mean some variant?
Anything that you want to implement. And since we covered ID3 in class, I would probably think about ID3.
Okay, I know a lot of people run into this slow, I guess.
Yes, so you can't just do ID3 trivially on this data because there are 70,000 features.
Right.
If you want to use ID3, you could do one of two things. Either change the feature space somehow, and you could do things like, if you feel like it, I'm not saying you should, you could do some sort of matrix. You can do projection to a lower space and just use a lower dimensional feature space. Or you could do something like random forests where you subsample features and subsample examples so that each thing becomes sparse.
Okay.
Or you could do decision stumps or decision tree with a depth limit so that you don't cover all possible things.
Okay.
So you have to do some sort of approximation. I don't see how you could do the whole thing, but it will take a long time.
Yeah, that's what I was
Yeah.
like, that's going to take.
Yeah, it's not good. It's not good.
Okay.
Yes.
If we do dimensionality reduction, is that something we have to implement on
No.
our own?
The general rule is any algorithm we cover in class, I expect you to implement it. Anything that we don't cover in class, you can use any libraries. Other questions about projects? So, just to we can now go back to the other thing that I left hanging, namely homework. Are there any questions about homework 4? Yes.
So the grad problem for the BC dimension.
Remind me what it was. It keeps changing all the time.
That one is prove that if the hypothesis space is a subset of another one, then its BC dimension
Oh yeah.
is less than.
Right.
So is that, do you want to prove that mathematically or is it graphically? Maybe we just be
I need a formal proof.
forward.
Yes. And the general idea, that one approach for this is to basically use the definition of VC dimensions. Write down the definition of VC dimension formally in math, and then you have an extra condition, and then that will basically give you the whole thing.
Okay.
And maybe it's kind of late to mention this, but every homework has an extra problem for grad students. Undergrads are welcome to try it. You're not going to get credit for it because those are the rules of the game. But that doesn't mean you should not take a look at it. And if you feel like solving it, come talk to me or the TAs, because these are questions that we kind of explore a little bit more. Okay, I'm going to move on. Another bunch of announcements involving talks. There are a whole bunch of talks in the next 2 weeks. 3 of them. And I think these are going to be fun talks, so you see if you can attend them. This Thursday there's going to be an AI lecture on robots. Next Tuesday, right after class, there's another AI lecture on human-aware artificial intelligence. Next Friday, there's going to be a talk on machine learning in space. I'll talk about each of these because I think all of them are cool. The Thursday's talk is at noon. It's in the web conference room, 3rd floor of web. It's Ben Kuipers from Michigan on making ethical robots. This talk is the second in this AI seminar series or AI lecture series that we have. If the talk doesn't excite you, there's pizza. Then next Tuesday there's a talk right after class, so I'll leave the class in a hurry. His name, he just goes by Rao, from Michigan, from Arizona actually, is going to talk about how AI can interact with people and in interesting ways. This one is also in the web conference room. It's at 11 on Thursday. And then the Friday after that, Oh wait, this one is next Tuesday. Yes. And then the Friday next week, that's the 16th. We have a School of Computing lecture. Kiri Wagstaff, who is at JBL, is going to talk about how she uses machine learning to make spacecraft faster, better, do more cool things. This is in the Union. It's at 11. Those of you who don't know Kiri, some of you may know her. She got her undergrad here at the U, and then got a PhD in the East Coast. I forget, was it Cornell? I think Cornell or Columbia. And then she was doing machine learning before it became cool. And she's awesome all around. So totally, you should make Kiri's an inspiration. I'll be reminding you about these things again. The one that I'll remind you about this also on Tuesday. And of course, I'll also remind you about all these other things. Alright, that's enough of a preamble for the class. Let's actually get to the class. We're talking about SVMs. We are trying to optimize this function. We are given a data set, and our goal is to find the best W. And by best, we mean the W, the set of weights that minimizes this expression. This expression consists of two parts. It consists of a regularization term. The first term is called the regularizer, which imposes a preference for generalization. It imposes a preference for larger margins. And the second term in this objective is called the loss function. In this case, for SVMs, it's the hinge loss. It basically imposes a penalty on classifiers for making mistakes. Or actually not just making mistakes, but for putting examples closer to the margin. So, and these two things are traded off by this hyperparameter 3. I'm not going to go into the details of this right now. I'm going to pick up where we left off. Namely, solving this using stochastic gradient descent. We've seen stochastic gradient descent a few times. So, and this was where we left off the lecture at the end of last week. We want to optimize this objective here, and I'm going to call that J of W. And in order to optimize that thing, we are given a training set, xi, yi, pairs of these kind, many of these, where x's are vectors. So, of course, as in all of these cases that we've seen before, we are assuming that somebody else has found a good set of features for us. This is kind of a annoying thing that happens in machine learning classes. We assume that feature extraction is somebody else's problem. And when you actually go and work on these things, let's say you work in the industry, you'll find that it's your problem. So there's not much insight that I have into that yet. Anyway, so we are given featurized version of the data, and the yi's are labels which are -1 or 1. And pretty much all stochastic gradient descent algorithms roughly work in this way. There's like a minor variation of this, which is actually the one that we implemented, that I'll get to at the end of this part of the lecture. This is not the version that's implemented, there's a different one, but this is the one that for which we have the theorem, so I'll first introduce this one. So, what you do is you initialize your weights. You initialize your parameters however you want. It doesn't matter how you initialize these things because the function is convex, so life is good. Later on, when we look at stochastic gradient descent for neural networks, the initialization becomes important, but we really don't have anything intelligent to say there. So let's say we initialize the parameters somehow. I'm just going to do it here, it says 0. And then you proceed in multiple epochs. At every epoch, what you do is you pick a random example. You sample an example uniformly at random from the training set, xi, yi, let's call it, and you pretend that this sampled example is the entire data set that you have. If that was the only example in the data set, then you can write down a loss function for just that example, so it would look something like this. So the loss function would be, you have a regularizer plus c times the loss over the entire training set. But the entire training set is just one example in this pretend world that we have, so it's just a loss on that one example. So there's no summation there. And what you do then is you compute the gradient of this loss function. So the gradient is just something that takes a function and produces a vector. Those of you who are not yet comfortable with gradients of functions involving vectors, I encourage that you get comfortable with it. We're going to do this a lot of times. But the gradient is a vector, and it points in the direction in which the function increases the fastest. And the idea is you update your w's in the opposite direction. So you update your w's, wt, you set it to be the previous w, wt minus 1, minus some step size, gamma t, times the gradient. The gradient is, keep in mind, a gradient of this fake data set that we have created using this one randomly selected example. Of course, if you do this one time, life is not good, because you're basically just, I don't know what you're doing. So instead, what you do is you repeatedly, you basically keep doing this again. Once you're done with this update, you put back the example into the big bucket of examples and you pick an example randomly. Maybe you pick the same one accidentally. You pretend that it's the entire training set and you take a gradient step. And you keep doing this till you are happy. What does happiness mean here? It means that you are convinced that the function is not going to go down anymore. So you basically, the value of the objective, the original objective on top has kind of stabilized and does not change. At that point, you stop these iterations and you return the final weight. Now, this version of stochastic gradient descent is, it comes with some rather interesting guarantees. In particular, this version of stochastic gradient descent is guaranteed to converge in expectation. It's guaranteed to converge to the optimum in expectation, which means if you run this long enough, you will get to the bottom of that hill, if you think about it that way. And the reason is because this function is convex. Because the original j is convex, there is basically there's a theorem which I'm not going to state or prove, but the idea is that this stochastic gradient descent will take you to the local minimum, in which case, in this case, it's the global minimum for a convex function. Now there are many variants. There are like so many variants of stochastic gradient descent. One important variant is this idea where instead of picking one random example, you pick a batch of examples. Maybe you pick 10 examples. Instead of a random example, maybe you pick a batch, small number of random examples. You pretend that this small number of examples is your entire data set. You write down a loss. This time the loss would have a summation over all those small set of examples, and you take a step. This version of this is called mini-batch stochastic gradient descent. It's not batch. Batch is like the entire, you compute gradient over the entire set of examples. That's gradient descent. It's not just using one example. It's somewhere in between, and it has somewhat better stability. And it tends to be the version that's used in practice. So let me talk about compare gradient descent and stochastic gradient descent. This is mostly an illustration for the next maybe 30 seconds or so. Anything I say is not rigorous. Imagine that you have this kind of level curves. So these are, we live in Utah, so people understand these kinds of curves almost intuitively. Basically, this is the inverse of the altitude, what do you call those things? Topographic maps. Yeah, exactly, thank you. This is the opposite of that, where circles are going down. Anyway, you know what this is. So this is a valley, and we want to get to the bottom of the valley. Gradient descent basically just follows almost a smooth path down to the bottom. Because we have in certain class of functions, we are guaranteed that every step we make is going to take us closer to the bottom. And that's a good thing, because if every step you take is going to take you to the closer to the bottom, and it's going to, and you know, some other properties are satisfied, you're guaranteed to get to the bottom. Now, stochastic gradient descent functions slightly differently. We want to get down to the bottom of the same valley. Instead, what you do is you pick a random point and you find a gradient. Now, the gradient of the original function may have pointed in this direction, but in this case, we are not using the original function to compute the gradient. we are using this hallucinated function where we just randomly picked an example and pretended it's the entire training set. So it may not point in the same direction as the true gradient. So we are not going down this true gradient, we are going down some other path. And from there, we find another gradient. We keep doing this. And this is like a drunk walk. Eventually, we'll get closer and closer to the bottom. Sometimes, we may even go the wrong way. Sometimes, we may have accidentally chosen an example that at that point is, it's because that it causes the gradient, the stochastic gradient, to point in the wrong direction from what we want, but in expectation, we will be making progress. This process takes many, many more updates than gradient descent. We will be changing the W's way more often, but we have to do less work to make that update because we are computing gradients of a much smaller function. And as a result, this tends to be more, overall, it tends to be more computationally inexpensive. There are actually some very cool guarantees about how computationally expensive it will be. And in fact, one very interesting paper from about 2007 pointed out that stochastic gradient descent or some variant of that can sometimes, for SVM for example, get to good enough weight vectors irrespective of how large your data set is. So in gradient descent, if you imagine you have 1 million examples, you have to make, compute the summation over all those 1 million examples to get one step. And then you do that again, and then you do that again. In stochastic gradient descent, maybe you don't have to touch all 1 million examples. Maybe even with a small number of updates, you've gotten close enough to the optimum, and it turns out that that tends to happen in some classes of functions. So in particular for SVM. So when we live in the land of big data, namely, I don't know what that means. If we have a large training set, stochastic gradient descent can take you faster to the optimum function value, and it does not. The guarantees do not strongly depend on the size of the data set. Which means as your data set gets bigger and bigger, a better thing to do is stochastic gradient descent. And as a result, today, pretty much most learning algorithms that you will encounter out there are one way or another based on stochastic gradient descent. That may be a good thing and a bad thing. It's a good thing because it works. It may be a bad thing because we are kind of optimizing our creativity is kind of channeled in only one direction. But maybe that's a challenge for you all. So everything is good, except, so let's see, we have the whole algorithm, we have this function, we can pick an example, we create a new objective for that example, and we have to compute the gradient, that thing, but that function has a max. And unfortunately, max is not differentiable. You can't compute the derivative of max, right? So we need to figure something out. So you see the problem here. So what's the derivative of respect to w of max of 1 minus of this is not a well-defined derivative because we have a function that is continuous but not differentiable, right? So the hinge is something that looks like it's 0 at some point and then it goes up sharply at this point. It's not differentiable, so we need to somehow fix that problem. Thankfully, someone else has already fixed that problem for us, and the answer to that. So yeah, the problem is that we can't take the derivative of that part in the circle there, or in that's shaded. And the solution to this problem that the maximization function is not differentiable is a very interesting idea called sub-derivatives or sub-gradients. And it's a generalization of gradients to non-differentiable functions. Have people seen sub-gradients before? Okay, good. So this is the one time where nobody raised their hand, or everyone is shy, which also happened when I asked you what is 99 divided by 100 in the morning. So I don't know what to say. Okay, that explains it. So we're going to look at this generalization of gradients to functions that are non-differentiable. Now, before you get all excited, this is not always going to work. It only works when when we have a function where the number of non-differentiabilities, the number of points where things are non-differentiable is finite. Conveniently, that's the case for the Henge laws. In addition, we still need the function to be continuous. So, if you have a function that is non-differentiable at an infinite number of points, this is not going to work. If you have a function that's not continuous, this is not going to work. So, I'm going to give like a impressionistic definition of subgradients because the details of it are going to take a little longer than we have. But intuitively, the one way to think about a gradient is to think in terms of tangents. So if you have a function like this, you can draw a tangent line. If you have a function in 3D, you have a tangent plane. If you have a function in d dimensions, you have a tangent hyperplane. At any point, you can find a tangent plane. I'll just call it a tangent. Now, what do we know about gradients and tangents? Gradient is basically the gradient is defined by the tangent, right? The gradient is the tangent. This is the tangent here, and the gradient here points that direction. Now, a convex function, one way of defining a convex function is to say that every tangent lies entirely below the function. In other words, for convex functions, the tangent is a hyperplane that lies always entirely below the function except at that one point that we are computing the tangent where it touches the function. We can generalize this to something called a subtangent. A subtangent is a hyperplane that satisfies the same point. Is any hyperplane that lies completely below the function at that point and touches the function at a point. So I'll give you an example by pictures. This example is from a lecture by Stephen Boyd. That's his name. I encourage you to go check it out. Boyd has written some of the best notes and lectures on optimization. I learned most of what I know about optimization by reading and watching Boyd's lectures. So, in some sense, we can think of a subgradient as a function as the slope of the hyperplane that lies completely below the function. Let's think about it. Let's formalize this. Suppose you have a function f. Yeah, you have this function f. Imagine that it is this curve here, and we have some point x at which point we need to calculate the gradient or the subgradient. The subgradient is always a vector. G. Let's call it G. Formally, a subgradient is defined to be any vector G that satisfies this property at every point y, which is not x, or it could be x. At x, that's not a problem. At every point, the value of the function, that's the point on the line, is always above the hyperplane. The hyperplane is defined by G transpose y minus x plus f of x. F of x is just the value of the function at this point. So what's happened is you have this function here, you draw a line that touches the function at this point, and the function at all other points is above. That's the definition of a subtangent or subgradient. Now, let's instantiate this definition to these 2 points x1 and x2. At x1, at this point x1, this function f is differentiable. So there's exactly only one line that satisfies this property, and that's the tangent line. And so there's only one gradient. The gradient is simply the standard gradient that we all know and love. So the subgradient is a strict generalization of the gradient. X2 is a point where the function is not differentiable. There's a kink in the function. So what happens is, there are many lines where this property holds. There are two G's, G2 and G3, where this property holds, and both these lines satisfy their properties. And not just two, but all these lines that go between these. This entire set of things are called subgradients. So at points where the function is not differentiable, the subgradient is a set. It's a set of directions such that the corresponding tangent, the corresponding hyperplane corresponding to that vector direction is always below the function. So there's more than one such thing, and because it's a convex function, if it's a convex function, because it's convex, we are all of these things, all these lines lie below the function. They are all subtangent. Now, does this make sense? Any questions about this before we go back to solving SVMs? Yeah. Was there a question there? Claire? Okay.
So couldn't you just choose like normal tangent that's to the left of it slightly, or to the right of it slightly?
You could. Yes, you could, but then you have to prove that it works. And in fact, this is roughly what we end up doing. That's literally what we'll end up doing. Because we have these. Let me zoom into this. Here, right? So the suggestion was, why do we bother with all these definitions? Why not just go to a point that's slightly to the left, and then go to this point here and find the tangent line there? Or why not go to the point slightly to the right, go to this point, I mean I'm zooming in, but it's going to be much closer, and find the tangent line there. And it turns out, and as this distance becomes smaller and smaller, we will get the two extreme subgradients. Anything in between those two vectors that you just described would be a subgradient. And in practice, we'll just use the extremes. Okay, so if you've not seen subgradients before, I encourage you to kind of go back and just, digest this idea a bit. The good news is that computing subgradients for many of these optimization problems that we'll encounter is actually very easy. For the SVM objective, the only problem case is the max function, right? And really, general strategy for computing subgradients for whenever you have the maximization is you solve the max and compute the gradients of each of these pieces. So I can write, let me write this more concretely. So you have max of 0, 1 minus yi, w transpose xi. This is really shorthand for either the value is 0 or the value is 1 minus yi, w transpose xi. When is it 0 is high, 0 is high, so if 0 is 0 equal to. When is it 1 minus y w transpose x? 1 minus y w transpose x is greater than 0. So there are only two cases, right? The function can either be 0 or it can be 1 minus y w transpose x. The good news is this is a continuous function, 0 is a continuous function, and this is a continuous function, and it's differentiable even. Both of these are differentiable in W. So what you do is you define the subgradient of this function. You define the subgradient of this function to be either 0 if 0 is greater than 1 minus y w transpose x, or the derivative of 1 minus y w transpose x, which is just minus yi xi, if 1 minus y I w transpose xi is greater than or equal to 0. So really, what's happened here is I want to compute the subgradient of this max function. Max is not differentiable, so I have to compute subgradients. And the trick, well, not the trick, the recipe, if you want, for doing that is first solve the max. So identify which side of the max you are on and just compute the gradient. And this basically instantiates the idea that was suggested where you go to the left or right and you pick the one that is, and both of these, the only problem point is really at 0. right? The only problem point is at 0, but at 0 both of these things, it doesn't matter which one you pick because both are subgradients. Both of these are subgradients at 0, so you pick one. It doesn't matter, and so life is good. And because there are only a finite number of these things, the optimization is not going to be hurt very much. So the general recipe for subgradient for maximization is you solve the maximization and then compute the gradient. Any questions? Yeah.
So the second part of this piecewise function of the subgradient is a vector. Do we treat 0 as a vector as well?
Yes, it is the 0 vector.
Okay.
It's the 0 vector in whatever dimensionality that you have. That's right. Yes, that's a good point. Yeah, that actually kind of slips through. Yes, it's the 0 vector. You will have to be comfortable deriving this by yourself. It's not magic. Just this one little thing that you have to keep track of. So what we have now is we have this function j, and its gradient is really either w, because we still have this part, right? It's either w by taking the derivative of w square, you get w. If 0 is not the max, so if max of these things is equal to 0, or it is w which still shows up here, minus c times yi xi, because c times the c is still there, c is a function. So the subgradient of this objective is itself defined in this sort of a case, using these two cases. It's either the loss is 0, in which case only the regularizer contributes to the subgradient, or the loss is not 0, in which both of them contribute to the subgradient, and one of these things has to be true. Questions? Yeah?
So, examining that, instead of subgradients, what if we modified the C term such that the gradient would be differentiable at all?
But it's not C that's the problem, right?
Well, I'm talking about that term, so the max.
Oh, you want to modify this whole thing?
Yeah, what if we square the max? Then it would be like a square hinge loss kind of
It's a
thing,
square hinge loss is a thing. Yeah, so we'll get to this maybe in a bit. Square hinge loss is a thing. Another modification is what is called the log loss, and that gives us logistic regression. Another modification is what is called the perceptron loss, which gives us actually perceptron. Another modification is what is called exponential loss, which it turns out gives us adipose. So a lot of these, there's a whole cottage industry of loss functions that are out there. And interesting you mentioned squared hinge loss. I usually don't have it in my slides, but when I first implemented SVMs, for some reason I took it upon myself to implement squared hinge loss. But I did it the most obnoxious way possible, so I will not teach it. Anyway, so yeah, there are variants of things, but when people say SVM, this is what they mean. Or not exactly, they don't necessarily mean this particular optimization, they mean this particular loss. So SVMs are hinge loss. So you can use another loss function that just is going to give you something else. Alright, so now let's put all these pieces together. And I'm going to show you the official version of stochastic gradient descent for SVM. I have the derivative, the subgradient up there just so that you have that in memory, or you don't have to memorize that. We are given a training set, we initialize the parameters to 0, and we proceed in multiple epochs. And now I'm going to show you a version that is actually implemented. I mentioned earlier that there's a version that for stochastic gradient descent that has a proof, and then there's a version that's actually implemented. The version that has a proof is where at every epoch you pick an example randomly, and you take a gradient, or in this case a subgradient step. In practice, what is usually done is you iterate through the entire training set. You don't pick examples at random, you iterate through the entire training set. You pretend that at every step, the ith example is the only example that you have. You write down the loss function for that one example, and you take a gradient. And the gradient is really the same thing here. So, in order to take the gradient step, what do we need to do? First, we need to decide what our gradient is. In other words, first we need to check if max of yw transpose x, max of 0, 1 minus yw transpose x is 0. When is it 0? It is 0 if 1 minus yiw transpose x is less than or equal to 0. Right? In this case, so you check. If this condition is true, then the gradient is just w. So then your update becomes w is gamma p times w. Otherwise, the gradient is this whole thing. So else, the update is the minus gamma t right? So one of these two things should happen. So either the gradient is w, in which case which will happen when yw transpose is greater than 0, in which case you just take a step in the opposite direction to the gradient, or yw transpose 1 minus yw transpose x is more than 0, in which case I made a mistake here, haven't I? It should be something's definitely wrong here. I know the next slide won't be wrong because I typed it out. So let me just move on. I made a negative basically you should have used negative instead of positive, but effectively what we have is if 1 minus yw transpose x is or yw transpose x is less than 1, then what will happen is that the gradient is w minus cyixi. So you take a step in the direction opposite to the gradient. So w becomes w minus the learning rate times w minus cyixi. But what is, let's just simplify this. This is exactly the same as w times 1 minus gamma t. The minus cancels out plus gamma t cyixi. Right? So that's this case here. And otherwise here it is w minus gamma p w, which is just w times 1 minus gamma p. Right? So what we have here is an entire algorithm for optimizing that objective. Yes?
It looks like you're multiplying the gamma, the 1 minus gamma is times the w,
Yes.
times the c yx.
That's right.
Yeah, that's what you're doing.
What do you mean they're not both not equal? Have I made a mistake here? It's entirely possible that I have, so let's see. Let me use
I think
the cases are switched. I know that the algorithm is right. I know the algorithm is right because I have implemented this enough number of times that I can just write down the algorithm without thinking of how to derive it. But let's see. And there's actually a very cool way of verifying that this is correct, and I'll talk about that in a minute. But really, what has happened here is I have w much. So in this case, the thing inside the bracket is the gradient. This is the subgradient. Right? If it's the subgradient, I have w times gamma w. Here, w times 1 minus gamma w. And then the gamma times c. I think this is right. So let me now talk about a few other implementation details. First of all, gamma t is a learning rate. There are so many tweaks possible. I'll give you a few examples later on. It turns out, just like with your perceptron, it's important to shuffle the examples at the start of each epoch. So let's just make that part of the algorithm. You shuffle the training set so that you don't go through the data in same order in subsequent epochs. And that's it. This is how we're going to convert. Before we go into the details, let's kind of examine this update. And I'll give you the reason why I know this update is right. I'm not actually thinking too hard about it. There are two cases here. This says I, W transpose xi is less than equal to 1. What does it mean when y W transpose x is less than 1? It means the current set of weights has put this example on the wrong side of the margin. If y W transpose x is less than 0, that means the prediction is wrong. If it's less than 1, but between 0 and 1, it means the prediction is right, but the example is within the margin. In both cases, we need to update the weights. And what does the update look like? Ignore the first term in the update, ignore this term here. The second term simply says, or rather, ignore this multiplier for now. The update simply says W is W plus something multiplied with y times x. So it's basically like a perceptron update. You're basically adding yx to the w if there's a mistake. But you define mistake slightly differently. It's like margin perceptron if you think about it. Those of you who have implemented margin perceptron, actually all of you have, right? So it's like margin perceptron, the margin is defined to be 1. But margin perceptron doesn't consider the other case. The other case says, even if there is no mistake, even if the example is put on the correct side of the margin, you still shrink your w's. Gamma is going to be a number between 0 and 1, so multiplying by 1 minus gamma basically shrinks the w's. In both cases, the w is shrunk, and if there's a margin mistake, you make an update. You do an additive update. What does shrinking do? So, remember, W transpose W, the norm, this quantity here, minimizing this, gives us a larger margin, right? Shrinking the W will reduce the value of this quantity because it multiplies it by 1 minus gamma squared. So, shrinking, irrespective of whether there is a margin mistake or not, you first shrink the W, and then if there is a margin mistake, you add yx or a scaled version of yx. And the reason this is good is because adding the yx basically takes care of making sure that our algorithm is making the right, is for the same reasons that perceptron did. It kind of rotates the hyperplane. Shrinking the w maximizes the margin, so it basically gives us generalization points. So adding the w gives us loss points. Shrinking the w gives us generalization points, and this one seeks to minimize both of these quantities. Now, the only thing that's left for you is that comes between you and an implementation is the learning rate. There are many options for the learning rate, but really the guarantee says for this algorithm says with enough iterations this will converge in expectation. Meaning if you run this forever, it will converge. Provided your learning rate satisfies certain properties. The properties are usually called square summable but not summable. What that means is that all your step sizes have to be positive, which makes perfect sense. Why bother in a negative step? The sum of the squares is not infinite, so if you add up all the step sizes all the way to infinity, if you add up the squares of the step sizes, so this quantity here, this is simply sum over gamma t squared, is strictly less than infinity, but sum over gamma t is tends to infinity. Now, this may seem like a weird thing, and this may seem like something that you have to work hard to find great, learning rate that satisfies the property. Thankfully, other people have done the job for us. You can prove to yourself that these values of gamma t satisfy those properties that we had. These two properties, or three properties really. In practice, there are so many more options for the learning rate. In your implementation, for example, for maybe your next homework, you'll implement SVM. I would probably ask you to implement one of these two things. Here you get another hyperparameter, gamma 0, which is the initial step size. So gamma 0 is called the initial step size, and then the step size keeps reducing every time you make an update. Yes?
So I know this is not like saying about model, but because it's similar to Perceptron, can we have
a similar mistake bound?
So it does not give you a mistake bound. There's no mistake bound per se. It doesn't exactly because it doesn't update only on the mistake. It updates no matter what. This is a batch output. And in fact, literally the next thing that I have is going to be about comparing Perceptron versus SVM. This was the theorem this is the result that I mentioned from about 2007. One could ask, how long should I run this till this thing converges or gets to within epsilon of the true optimum? Let's say there's a true optimum and I want to get a function value that's within epsilon. And it turns out for strongly convex functions, you don't have to remember any of these things. I just want to point out one thing, which is, if you have n training examples, gradient descent takes order of n steps, so order of n steps, order of n steps to get to within epsilon of the optimum, whereas stochastic gradient descent does not have a dependence on n. So you can get to within epsilon of the objective using a number of steps that doesn't depend on how many examples you have. And when I first saw this result, I was amazed. So it doesn't matter how big your data is, you run stochastic gradient descent for how many steps, for a certain number of steps that doesn't depend on the number of examples you have, but only depends on the dimensionality, and you're guaranteed to get to within epsilon of the optimum. But in general, when your data size is large, the one-line summary is prefers stochastic gradient descent. The other thing is based on, there are, because stochastic gradient descent has become so widely used, there's been a lot of research on how do you pick good step sizes. This whole summable but square summable is a guarantee that's needed for convex functions. When we go to neural networks, we'll see that nothing we have is convex. But we need other learning rate ideas that can take us faster, let's say, to the minimum. And you may have heard of some of these words. We won't cover any of these things, unfortunately, but you can look it up. And essentially, what you should keep in mind is these are all methods for deciding what's the step size, what's the learning rate. So there's ADA-grad, ADA, delta, RMS prof, nest prof, gradient, momentum. These days, most people who use neural networks for the last year or so use this thing called Adam. But maybe that won't last next year. Tomorrow we'll have something else. So there are many, there's a whole cottage industry of learning rates. So just to quickly wrap up, or at least this part of it, the stochastic subgradient for SVM is this algorithm. You have a training set, you initialize your weights, you proceed in multiple epochs, you shuffle your training set, and you iterate through every example. And for every example, first you check whether using your current weights, YW transpose X for that particular example is less than or equal to 1. If it is, you make an update. And the update consists of two parts. First, you shrink the W by multiplying with 1 minus gamma, and then you add gamma C YX to the shrunk weights. If it turns out this margin condition was not, the criterion was not met, in which case the example is correctly classified on the correct side of the margin, you still shrink your W so that you get better generalization. Okay? And you do this enough number of times, so let's kind of list out all the hyperparameters that we have. We have T, we have C, and then for the learning rate, you will have an initial learning rate, gamma 0, because gamma T could be gamma 0 divided by 1 plus T. So you have gamma 0. All of these are hyperparameters that you have to find how? Cross-validation. You do cross-validation, you can use a validation set to decide which T is good enough, when to stop, but for C and gamma naught, you use cross-validation, and that's roughly how it works. Any questions before we start looking at comparing this to Perceptron? Yeah?
So does this algorithm specifically look at each example in the training set as opposed to the one that you showed us where we only choose a subset?
That's right. That's exactly right. The example that I showed you, there is a certain probability that an example will never be seen by the learning algorithm. Just make sure that every example is at least seen. Yes.
And then, in that case, the big O does depend on.
In this case, the result, that's what I meant by the results are for that one,
Right.
whereas the implementation is usually this one. Other questions? Yeah?
For perception, we have like everywhere it leaves a static learning rate. Would this algorithm completely break if we used it?
If you use a static learning rate, your learning rate is no longer square summable. Because if you add up, you have to be careful. So you need that property. In fact, even for Perceptron, based on what I'm going to say next, even for Perceptron, I would prefer a decreasing learning rate. The original algorithm for which we had the mistake bound proof has a static learning rate, but if you want these sort of batch kind of guarantees, it's better to use a decaying learning rate. So let's compare to Perceptron. And I mentioned at the beginning of this part of the class, or this when we started stochastic gradient descent, the Perceptron algorithm and this one is roughly about 12 characters different. Let's see if I was right. So there is one difference here. There is another difference here that does not have that, and then there's this. Okay, it's more than 12 characters, but that's it. That's the diff. So, in some sense, the perceptron algorithm is extremely similar to what we have. In perceptron, what you do is, by the way, when I say perceptron, I mean the batch perceptron, not the online version. In perceptron, what you do is you check whether you made the current parameters have made a mistake, and if so, you say W is W plus some learning rate times Yx. Here, what you do is instead of checking for mistake, you check if the margin criterion is violated, namely if YW transpose X is less than 1, in which case you just say W is a shrunk version of W plus some step size times C, there's also a C here, which is another difference, Yx, otherwise you still shrink the W. Now, it turns out, so we came to these two things in very, very different ways. In perceptron, I just said, here's an algorithm, and then we can prove things about it, and it seems to work. For the SVM worldview, we didn't just invent an algorithm. In fact, this is not the only algorithm for optimizing SVMs. This particular algorithm, the way we came across it is, we started off with this whole VC dimension, margin, the hinge loss, and then the subgradient, and this is just a much longer route to get to something that looks very similar, and this brings up the question, maybe there's a way of bringing up perceptron this way too, and it turns out there is. So SVM optimizes what's called the hinge loss. You know the hinge loss, it's max of 0, 1 minus YW transpose X. But it also has a regularization. It turns out you could have derived perceptron from scratch by saying perceptron optimizes a different loss function called the perceptron loss. The perceptron loss is max of 0, minus YW transpose X. So this is the big difference here. There's no 1. And there's no regularization. So you implement stochastic subgradient descent, and this is a good way for you to kind of test your understanding of subgradients. Derive the perceptron algorithm by minimizing the total perceptron loss without regularization. You should get the perceptron algorithm, and that is a good way for you to confirm that you understand subgradients. So it turns out that perceptron can be seen as another learning algorithm that minimizes the perceptron loss. But I'll get to that in a minute. Just a summary of SVMs from an optimization point of view. SVM minimizes the regularized hinge loss, which is convex. We can use any convex optimizer to solve it. One of the most common optimization techniques for solving it is called stochastic gradient descent, or rather it's stochastic sub-gradient descent. It runs really fast, and it's widely used, it's easy to implement. You should kind of know how this compares to the perceptron algorithm. And the convergence criterion is a bit of an issue. You have to be careful to see when it converges, and that capital T, the number of steps, you have to think about it carefully, because this particular update can be rather aggressive at the beginning and get you to a reasonably good weight very quickly, and then make minor changes that are not, and then slow down basically the learning rate. The rate of convergence slows down as you run this longer. So there are other tricks. But the other point is, this is not the only learning algorithm for minimizing this loss. Probably one of the other most common methods for minimizing the SVM loss uses what is called coordinate descent in the dual. It's a different learning algorithm, and sadly I can't go into the details of that because I'm not going to be talking about duals at this point. But those of you who may have used or heard of this library called liblinear for SVMs, basically liblinear implements coordinate descent in the dual, and it's also super fast. Anyway, so there are other methods for doing this. Today, most people just implement stochastic gradient descent because it's so fast. Any questions about this? About this whole thing? Yeah.
So gamma naught and C are both scalars, right?
That's right. They're both real numbers.
So could you just treat the hyperparameter as just T and then C gamma naught? Or no, I guess you can't not in the.
You can't, right? Because you need on the other side you have a gamma.
No. Yeah.
Alright, so I'm going to ask you to revisit, like all lectures, I want you to revisit these things and kind of derive it on your own just to convince yourself that I did not lie to you. I'm going to take what we saw today and generalize it a bit more and introduce you to this, what might be the most dominant strategy for inventing learning algorithms today, which is to frame learning as loss minimization. So the setup looks like this. Suppose we have some examples that are drawn from a fixed but unknown distribution T. And let's say there's some classifier, an oracle function f that we don't have access to, but it labels examples for us. And our goal is to find a hypothesis that mimics the test. This is the same setup that we've been doing all this while. Now, in the ideal situation, the philosophy here with risk minimization, it's also called risk minimization or loss minimization, is we define a function, L, called the loss, that penalizes bad hypotheses. So, learning is search over hypotheses, right? So we have all the functions that we care about, and this loss function penalizes functions that are bad, hypotheses that are bad. And our goal is to find, the goal of learning, one way of thinking about learning is to say, I want to find a hypothesis, a classifier if you want, H, that minimizes expected loss. Expected how? Expectation according to this fixed and unknown random distribution. In other words, we want to learn by minimizing the expected loss of all functions. This is a nice idea in theory. It's kind of a satisfying idea because it says, I know that this is the notion of mistake, this is how I define mistake, and my goal of learning is to make the fewest mistake, or not mistake, but I'm going to define penalties for misclassification or misprediction, and I'm going to find the classifier that has the lowest expected penalty. The problem here is the distribution D is unknown. We don't know the distribution, so what do? The solution is we don't care about the expectation, or we can't compute the expectation. Instead, we minimize the empirical loss on the training set. The training set is drawn from this distribution, right? So I can calculate, in some sense, this is by saying the average loss on the training set, as the number of examples goes up, tends towards this expectation. This is the law of large numbers. So as we get more and more examples, the average loss is going to look like the expectation. So might as well just minimize the empirical loss on the training set. So this idea is called empirical loss minimization or empirical risk minimization. There are certain textbooks in machine learning where they start off by saying, we are now going to look at machine learning. Chapter 1, Section 1, empirical risk minimization. It is such a dominant idea. It's basically the idea that pervades most modern machine learning because it gives us this almost a recipe for building learning algorithms. We don't build learning algorithms anymore, we build loss functions. Okay, that's also changed once neural networks came along, but we'll get there later. So, the goal of learning is to minimize empirical loss on the training set. Now, do you see a problem here? Yeah, overfitting is a problem because I can get you a function that gives you zero loss on the training set. The training set itself. Put the training set in a table and I'll call it the table classifier. Every time a new example comes in, I will look at my table and see if the example is there, in which case I'll predict the label, otherwise I'll give you just random nuts. That's going to have zero loss on the training set and it's not a particularly useful thing. We have to deal with overfitting. We need something that biases the search over hypotheses towards generalization, towards simplicity, if you want, towards some way of improving predictions in the future. Now, this is essentially, we need some way to capture Occam's razor. What does that? Any function that does that is called a regularizer. A regularizer is a function that penalizes complexity. It penalizes complexity in one way or another. So this gives us a new and more modern way of thinking about learning, which is not just empirical loss minimization, but empirical regularized loss minimization. So the goal of learning is no longer just to find a hypothesis that minimizes loss or empirical loss, but to find a hypothesis that minimizes the sum of two things, a regularizer plus the empirical loss, and these two things are traded off by some trade-off parameter, let's call that C. This must look awfully familiar. In fact, some of you are probably thinking I'm just slacking off by redoing the same lecture again. But it turns, of course, we've seen this before, and one regularizer is for linear classifiers, one regularizer is the squared loss, squared norm regularizer, which imposes a preference towards larger margins. But we still have an opportunity to pick different loss functions. A loss function is anything that penalizes mistakes. We'll not talk about regularizers much today, or in fact, pretty much for the entire semester, simply because that's a door I don't want to open. But if that's what interests you, you should take a look at it. Let's talk about loss functions. A loss function is something that penalizes mistakes. We are minimizing average loss of training set. So the question that I want you to think about for about 30 seconds, or maybe so, is what is an ideal loss function? What is the loss function that you would like minimized if computation was free? You have to penalize mistakes. Let's think about the following loss function. Every time your hypothesis makes a mistake, it loses 1 point. If it does not make a mistake, it loses 0 points. Right? We have already seen that before. This is called the 0-1 loss. The 0-1 loss is simply a penalty that increases, that counts the number of mistakes. If our goal is to minimize the number of mistakes, then we should be optimizing this quantity, right? You can write that in general by saying the prediction is not equal to the ground truth, then the loss is 1. For linear classifiers, we have a clean way of defining mistakes, which is yw transpose x is less than 0. So I can say the loss is 1 when yw transpose x is less than 0, otherwise it's 0. That's the good news. We are able to write down what we want mathematically. That immediately takes us to the bad news. This is intractable. It's computationally intractable to minimize this loss function. So we need to do this, the one thing that we always do when we face a problem in math, which is we make some assumptions. In this case, we are going to make an assumption that this is not the function this is the function I want to minimize, but I'm going to assume that I'm going to find a surrogate that's good enough. Right? So this is what the 0-1 loss looks like for linear classifiers. If I plot yw transpose x on the horizontal axis and the loss on the vertical axis, on this side there's no misclassification, so there's no loss. On this side there is a misclassification. This is for one example. You have a loss of 1. the hinge loss is a surrogate for the 0-1 loss. And we've seen this before, so I'm not going to spend too much time talking about this. The support vector machine is basically, from this perspective, we've basically reinvented support vector machines now. Instead of going to the whole BC dimension, blah, 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 what we're saying is, I want to minimize the 0-1 loss. It's not easy, so I'm going to invent a surrogate that essentially over penalizes. See, the SVM loss is always more than the hinge loss. So it's better, it's a more conservative loss if you want. So it over penalizes, that's the hinge loss, and so you can use this, and there are, then the whole algorithm and the theory and everything just follows through. Questions? This is not the only loss but from this perspective, what makes hinge loss special? This is just one thing. Maybe other surrogates exist. But we get the SVM objective, we have the regularizer and the empirical loss, and then there's the hyperparameter that trades off between them. But maybe other losses exist, and they do. It turns out, I just have 4 here, but there are way more losses than I can put on a slide. We just looked at the perceptron loss. The perceptron loss is defined to be max of 0, minus y to the transpose x. We've seen the hinge loss. Very soon after the AdaBoost algorithm was invented, I can't remember the citation right now, but there was a proof that said, actually this algorithm is minimizing what's called the exponential loss. It's another loss function where every feature is a weak classifier. If you think of every feature as a weak classifier, then the AdaBoost algorithm is actually minimizing the exponential loss. I could define another loss function called the log loss. The log loss is just another surrogate for the 0-1 loss, and it turns out minimizing that gives us the logistic regression algorithm. How many of you have seen the or heard of logistic regression? It's rather popular. Turns out it's just another surrogate for the 0-1 loss. If you want to plot them on a graph, and this will be the last thing I do, we want to minimize the 0-1 loss, the regularized empirical 0-1 loss. That's not going to work. Instead, we could use the hinge loss, and that gives us the SVM algorithm. We could use the perceptron loss, and that gives us the perceptron algorithm. We could use exponential loss, and that gives us AdaBoost. We could use the log loss, or logistic loss, and that gives us logistic regression. And there are many others. Now, I'm not going to spend any time going over the details of these things. I expect you to go over the details of this offline. But just to wrap this up, the framing learning as minimizing regularized loss is the dominant idea in machine learning today. And the story goes, if I want to invent a learning algorithm, I'm not going to invent a learning algorithm. I'm going to invent a loss function. And by inventing a loss function that is both tractable, namely it's convex and it's easy to optimize, I can use stochastic gradient descent or any optimization problem and I get a learning algorithm. So I'm not going to invent a learning algorithm because that's somebody else's problem. I'm going to invent loss functions. All these losses apply not just to linear classifiers but also to other models. You just don't minimize loss, you also regularize because you want to generalize. This idea is widely applicable, we'll encounter this multiple times again. Alright, I'm a minute over time, so I'll stop right now. I have office hours at 4 o'clock today. Now,